after you finish your talk, then we stop the recording and then we have the discussion. Okay. All right, Kevin, please. The floor is yours.
Lovely. So hopefully everyone can see my screen okay. Just move the bar up so I can see my screen. Yeah, so this is some joint work that's now a paper, and I'll share the archive link to the paper at the end of the talk. But it's on Bayesian aggregation, also known as Bayesian reconciliation of distributions given by experts, which I've called expert priors here. And in particular, it's going to be in conjunction with the probabilistic Delphi method. So I'll have to talk a little bit about what that is as well. But it's joint work with Malcolm, who was my PhD supervisor at Newcastle many years ago, Simon, who's here, and David Hartley, who works at GSK but did a PhD with Simon. Okay. So 2 slides of motivation. So a couple of things that I've been working on over the last few years. The first one I talked about in this seminar series a year and a half ago, something like that. And this is the UK climate resilience demonstrator. So this is a digital twin trying to look at the possible effects of extreme weather events caused by climate change on infrastructure networks in the UK. So this is work I've been doing with Jim Smith and at Warwick and Chris Dent at Edinburgh. And the aim of this climate resilience demonstrator is to come up with a digital twin that helps us to improve climate resilience, to essentially look at decision support and to improve climate resilience across infrastructure networks in the UK. And the infrastructure networks are the water network, the power network, and the communications network. That's what they're looking at. And so Jim, Chris, and I have been looking at how to model in an extreme weather event. So we started off with flooding in year 1, and we're now looking at extreme heat in year 2. Essentially, if we know how much water is building up outside these assets, what's the chance they're going to fail? So how do we get from there to possible failure modes? So model the probability of asset failures of individual assets within a larger network. And that, of course, can then cause cascading failures. And so the way that we've approached this is to build Bayesian networks of the possible routes to failure from an extreme weather event for a particular asset. So there's an example of one at the top of the slide here, and I'm not going to go into the detail of these today. But the upshot was we needed to elicit probabilities to quantify these Bayesian networks. So to quantify the conditional probability tables within these Bayesian networks that we'd constructed, again, also based on expert judgment. And so in year 1, I sat down with panels of experts from the different infrastructure networks, so the water network, the electricity network, etc. And we elicited the probabilities for the conditional probability tables using the Sheffield method. And I'll very briefly touch on what the Sheffield method is on the next slide, but this is my go-to method. We all have our sort of favorite method. This is how I do elicitation in most of the times that I've done it. And so this is just sort of my standard practice. But I got some pushback against this. And in particular, as we're trying to sort of extend this and build up to larger networks, so think networks of sort of 200 assets, so 200 different pieces of kit within an infrastructure network. One of the engineers who's responsible for the next stage of the project said to me, this process is not scalable. So this is copied and pasted directly from an email to me. And doesn't lend itself to more digital/software-based elicitations that might be used in the future. So in other words, in year 2 and onwards, I'm not allowed to use the Sheffield method. So I'm going to have to do something else for the elicitation. So at the same time as this, I've been working on the first year of something called the Holy Food Project. And so this is a Horizon 2020 EU grant. And the aim of this project is to come up with early warning and emerging risk prediction systems to identify and monitor essentially emerging food safety risks in the food chain. So this is trying to work out where the next sort of possible danger to human health is in the food chain. So this is sort of work related to the EFSA stuff, essentially. And they're doing lots of cool things. They're doing AI modeling, they're doing machine learning, they're doing data scraping and then textual analysis and all sorts of clever stuff. But at the end of the day, they can't get data on everything they need to try and work out these sort of risk assessment models that they're interested in. And so they're going to have to do some elicitation as well, which is why I'm involved in the project. And so the sorts of things that we're going to have to elicit, and we're going to start doing this early next year, are things like the probability that a candidate emerging risk, something that's come out of these clever AI models or whatever, is actually realized and becomes something which is a problem in the food chain in Europe. But then they've also got these risk assessment models, and they have inputs, and of course they do. All models have inputs. And for the inputs that they don't have data for, they still need to pick values of these inputs to run their risk assessment models. So they need uncertainty distributions on some of the inputs to these risk assessment models that they don't have data on. So again, there'll be some expert judgment elicitation there. And again, my go-to would have been to use a Sheffield type approach, get some sort of consensus distribution from a group of experts. But within this project, there's quite a lot of social scientists. And they have quite a strong negative reaction to things like the Sheffield method. So again, this is another copy and paste job from an email sent to me from someone on the project. So they much prefer Delphi type approaches, and in his words, to avoid the negative effects related to interpersonal biases, strong personalities, defensive attitudes, and unproductive disagreements. So they don't want to get the experts in the same room talking to each other. That's the upshot of this. So again, both of these projects, they don't want the sort of elicitation I would normally do. So then the question is, well, what sort of elicitation do I think I should do, given that I'm not going to now use the Sheffield, the shelf type approach? So first of all, I'll talk a little bit about, very briefly, about the Sheffield method, because I think most people probably know quite a lot about it already. So the Sheffield method is a consensus method. You get the experts in a room or perhaps a Zoom chat like this, all together at the same time, and they discuss stuff and try and come to consensus. The main steps are sort of given at the top of the slide here, but I'm just going to go through the bullet points rather than go through those individually. Essentially, there are two stages when you use the Sheffield method. Before the experts interact with one another, you do an individual elicitation, so the usual sorts of things, quantiles of their uncertainty distributions. There's then a group elicitation, which is eliciting, again, maybe quantiles or probabilities or something in order to get a consensus distribution. In between those two different stages, there's discussion between the experts. So we reveal all of the judgments given by the experts in the individual elicitation, and they discuss differences. They talk about the evidence they use. They talk about their rationales and their sort of scientific model that's working in their head, before hopefully coming to some sort of group consensus, and hopefully that corrects errors. It perhaps brings the experts closer together in terms of their judgments. And then at the end, rather than say all the experts agree, we elicit the opinions of a rational, impartial observer, some hypothetical person in the group elicitation part. So that's what I would normally use. In these two projects where they're not keen on the Sheffield method, the thing that I thought I might use is some version of a probabilistic Delphi method. So this is the sort of third method alongside the classical method and the Sheffield method that EFSA recommend, for example. So how does the probabilistic Delphi type method work? Well, it's essentially a specially tailored Delphi approach, and Delphi methods basically means you do things in a number of rounds. So in the probabilistic Delphi method, in round one, with each of your experts, I've got three experts here, you would perform an individual elicitation to get your hands on their individual uncertainty distribution, or perhaps prior distribution if you're a Bayesian. You would then, somebody, so that would be me in this case, would then collate all of that information, and together with the distributions, you would also have written rationales from each of these experts. So why did Annabelle, who this expert is, choose the values she did? Why did this lady choose the values she did, and why did he choose the values he did? And then you would share all of the elicited values from each of the individual experts, anonymized, alongside the anonymized rationales, associated with each of the fitted distributions, with all of the experts there, and ask the experts to reconsider, to have another think about their judgments, and then you do another round of individual judgments, collect them together again, share the anonymized versions, and perhaps even have a third round as well. So the idea of Delphi is that through the sharing of the rationales and through looking at the values other experts are given, perhaps the variability, the variation between the different distributions reduces over time. And so by the end of round 3, you've got a set of judgments which are perhaps closer together than at the end of round 1. And from the experts, that's the sort of rationale behind these things. I do like the idea that the experts get to share information. I think this is an important part of elicitation. So they're interacting with one another, okay, in this more limited fashion. At the end, though, you've still got, if you've got 3 experts, you've got 3 different distributions. And for your risk assessment model or whatever it is, you may want to have just a single distribution summarizing your group of experts somehow. And so in the probabilistic Delphi, certainly the way it's set out by EFSA, you're going to use some sort of mathematical rule for consensus, and the recommended one seems to be equal weighting. So I quite like this idea of this probabilistic Delphi. I don't think it's a bad approach. But I don't like this idea at the end that we just use an equally weighted linear pool for the aggregated distribution. That seems like a little bit of a cop-out to me. So I began thinking about what you should do instead. And of course, you could do lots of things. For example, at that stage, you could then use the classical model to weight the experts and weight them using the classical model. But I went down a slightly different route with Malcolm and Simon and David. And so that different route is really the main part of this talk, the bit that I'm going to talk about for most of the time today. So the idea here is that instead of using some sort of linear pool where you give each expert a weighting and then average the distributions in a sophisticated way, instead we're going to use something called Bayesian reconciliation or Bayesian aggregation to do it instead. And so you are still, in some sense, going to get some sort of combination of the expert distributions, but the combination rule is just a little bit different. So Bayesian reconciliation's been around for a long time. In fact, it's been around for longer than me. Both those dates are before I was born. But it hasn't been implemented very much in practice. So this is an attempt to put together a version of this which is easier to implement and which we can do relatively quickly and straightforwardly. For example, at the end of a probabilistic Delphi method. So let's suppose we're in a sort of standard elicitation situation where we've asked each expert for each quantity of interest, so I is expert I, J is quantity of interest theta J, for a measure of centrality, so their median, and then some interval, so a lower quantile below the median and an upper quantile above the median, L and U. So in the classical method, this would usually be the 5% and 95% quantiles. In Bayesian aggregation or Bayesian reconciliation, then what we do is we treat each of these quantities specified by the experts as data. We treat them as data, so they're information, and we treat them as data as if we've observed them. So we're observing what the experts say. And what that means if we do that, then that means we can use Bayes' theorem in order to combine the judgments from the different experts. In order to do that, we need somebody who isn't the expert. So we tend to term that person the decision maker. Lindley called them the investigator. And the idea is we're going to represent their beliefs, having seen what the experts thought for their medians, lower and upper quantiles. So we imagine we have a decision maker who, before the experts give their judgments, have their own probability distribution, their own uncertainty distribution about the quantity of interest theta J. And if the decision maker isn't an expert, that could perhaps be something which is relatively flat and not very informative. And then the decision maker is then going to observe the vector of lower quantiles, the vector of medians, and the vector of upper quantiles from each of the experts. So the 3 quantities that we've elicited from each of the experts. And we're going to end up with, by combining the decision maker's prior distribution with the likelihood of observing these 3 different things, given by this term here, we can then update the decision maker's beliefs about the quantity of interest and get the decision maker's posterior distribution. So pi of theta given L, M, and U is the decision maker's posterior distribution for theta J, having observed the quantiles specified by each of the experts. And so this is quite a neat idea. It's quite a nice thing to be able to do, but it does require that we can write down this thing here, this F. So this is the decision maker choosing a likelihood of observing all the lower quantiles that they have, all the medians and all the upper quantiles from the experts, given some true value of the quantity of interest theta j. And so the difficulty with Bayesian reconciliation or Bayesian aggregation is specifying this likelihood function here. And this is the reason that it hasn't really been used much, because you need to make some sort of assumption on the likelihood function. But if you can do that, then this is quite a nice thing to do potentially, for two reasons at the end of the probabilistic Delphi method. The first is that it gives you a natural interpretation of what you end up with. So the experts have given us all these elicited judgments. What does the combined, the aggregated distribution actually represent? Well, it's a subjective probability distribution representing the judgments of the decision maker, the beliefs of the decision maker on the quantity of interest, having heard what the experts have had to say, having heard the information elicited from the experts. So you've got a nice direct interpretation there. Perhaps an even better reason that this is a nice thing to do is within this likelihood function here, what we can do is we can incorporate the fact that through the information sharing in different rounds of the probabilistic Delphi method, and also through perhaps some sort of evidence dossier that you'll have compiled and given to the experts in advance, the experts are almost certain to be giving you dependent judgments. So they're not going to be giving you independent judgments from one another. The amount of information in the experts' judgments is less than the number of experts that you've got. And so what you can do is you can incorporate this dependence between the judgments being given by the experts within your likelihood function, within your Bayesian model structure when you're performing this Bayesian update. And so that's essentially the key thing in what I'm going to talk about when I talk about a specific Bayesian model for how to do this in a minute. Okay, so the way that we're going to do this is using Bayesian hierarchical models, because they're fast and efficient to compute, and they allow us to investigate nice flexible dependence structures between the judgments expressed by different individual experts. So we're going to now set up a hierarchical model which is going to allow us to do this Bayesian reconciliation, to update the decision maker's beliefs in light of hearing the experts' quantiles. So first of all, some notation. So suppose we've got an expert I, and now we've got an extra subscript here, which is going to be group little g for quantity theta j, provides their lower quantile, their median, and their upper quantile. So the reason we've got this extra group subscript is that often naturally experts will fall into a small number of groups. So either they relied on the same evidence and interpreted it a similar way when they came to their judgments. Perhaps they're particularly vulnerable to the same biases in giving their expert judgments. Or in this probabilistic Delphi method, perhaps what's happening is when they see the rationales and the numbers from other experts, the experts are sort of naturally agreeing with some of the other experts and sort of clumping together in a small number of groups who are using similar rationales to come to their judgments. So you could imagine this group then coming naturally as the rounds of the Delphi process persists. And the reason that we want to include a group subscript here is that what we want to do is we want to say that the judgments from experts within the same group are going to be more highly correlated than the judgments from experts between different groups. So experts using the same rationales to come from their judgments are going to be giving you more correlated information than experts who are relying on different pieces of evidence, who are using different rationales, who have a different mental model, if that's a nice way of thinking about it. So then we can just use sort of standard hierarchical model structures in order to incorporate this dependence and to get out the decision maker's posterior at the end. So first of all, if we consider the medians given by all of the different experts, then we say the median for expert I in group G, just comes from a normal distribution centered on some overall mean for all the experts in group G with some variance. And then we have a group level in the hierarchical structure. So the mean for group G just comes from a normal distribution with some overall mean, mu. And then we have the decision maker level. So the bottom level here is the decision maker's belief. So before they observe the data, the decision maker would have a normal prior distribution for the median centered on some value with some variability. So this would mj and vj bar would represent the decision maker's beliefs. And then we've got the two levels of the hierarchy, the individual level and the group level. And we probably want to learn about the variability between experts within a group and the overall variability. So the individual level and group level variability. And if we give these prior distributions, which is what we'd have to do to learn about this variability, if we give them inverse gamma prior distributions for these variances, then if we're going to use MCMC, we have some nice conjugacy there, and it's going to make our MCMC sampler run in seconds rather than minutes. So we can use nice relationships there. So we could use a similar hierarchical structure for the lower quantiles and the upper quantiles specified by the experts. But if we do this individually with no constraints, then it could be that in our aggregated distribution, sometimes the median is below the lower quantile, or the upper quantiles below the median. It won't naturally respect this ordering that the lower quantile has to be below the median has to be below the upper quantile. So rather than have a hierarchical structure directly for these other two quantiles, instead I'm going to define the distance between the median and the lower quantile, call that D1, and the distance between the upper quartile and the median, call that D2. These can take any value, and whichever value they take, the final aggregated quantiles are still going to respect the relationship. L has to be below M, M has to be below U. So instead of aggregating L and U directly, we're going to
may I ask a very quick question? Those distances, won't they be equal if you're assuming normal distribution?
They won't in general be equal because the experts will have specified them, and they won't have been assuming a distribution when they specified them. This is their judgments. So for the distances, these are positive. So we take the log of them and assume that these are normally distributed for the purposes of the hierarchical model. So then the log of them can take any value. So normal is then a reasonable thing to think about. So again, we've got the individual level. It's exactly the same as the medians. Now I've defined the distances. We've got the individual level at the top. We've got the group level in the middle. And we've got the decision maker level, the sort of overall level at the bottom. And so the delta kj's are going to give us information about these two distances. And then, of course, because the distances are just nice simple functions of u, m, and l, we can then just recover u, m, and l in the way that I'll show you at the top of the next slide. Again, we probably want to learn about the variability parameters. So we want to give them some prior distributions. And if we give them inverse gamma prior distributions, we get a bit of conjugacy, which speeds up the MCMC. Okay. So then from the model parameters in the bottom level, which is the decision maker level, this is going to be the decision maker's beliefs having observed what the experts have told them. Then, well, it's quite easy. The median is just equal to the mean in the overall level, so mu j. And then we just need to reverse these two functions here to make u and l the subject of them. And if we do that, we just get these two equations here. So once we have run the hierarchical model and got samples from our posterior distribution, we just push them through these two equations here. And that gives us samples of the posterior distribution of the decision maker for the median M, the lower quantile L, and the upper quantile U. So we obtain these samples via Markov chain Monte Carlo methods. I used RJAGs in R for this task, but you could use your favorite software for doing that. Then we've got samples from the decision maker's posterior distribution, which is going to be our aggregated distribution. So we have to somehow have some distribution which has these three quantiles here. So we could fit a norm-parametric distribution, we could fit whichever distribution we wanted. In this paper, just so we've got something that we fit so we can actually implement it in practice, I suggest fitting something called a shifted log logistic distribution to the three quantiles. So it has a slightly nasty looking PDF, but the reason that this is quite a nice distribution is, first of all, that it has three parameters, a gamma, a sigma, and a mu, so shape, scale, and location. And so that means we can take into account both the central tendency, the variability, and the skewness specified by the expert. So that comes out of this hierarchical model. So we've got three sort of degrees of freedom in our fitted distribution. But the second reason that this is nice is because we can solve for the parameters in closed form. So what we're going to be doing here is we're going to have 10,000 samples, which are an L, an M, and a U in each of the samples, and we want to fit one of these distributions each time. So we're going to be fitting a distribution 10,000 times. So being able to solve for the parameters in closed form from some quantiles saves us a lot of time and energy rather than having to use some sort of numerical method. So this has a nice closed form quantile function that allows us to then write down the equations of each of the parameters in terms of the quantiles in closed form. So this is a nice sort of starter for 10 in terms of a distribution to fit. So in that case, what we can do is we can use samples of L, M, and U to obtain samples of theta j, just using this shifted log logistic distribution form. The final step is related to this idea that when you're asking in elicitation, when you're eliciting different quantities, so multiple thetas, so theta 1 to theta n or whatever, often the quantities of interest, the things you're eliciting, are going to be on very different scales. They're not necessarily all probabilities or all continuous quantities that take any value. It seems sensible with a hierarchical model like this to work on the same scale for all of the different quantities, not least because then when you're sort of characterizing the prior distributions, you could do so in a sort of standard way rather than having to scratch your head and work quite hard each time you do it. So in order to do that, we use an idea that Simon developed with Michael Wiper in the 1990s, I think. And the idea here is that we take the quantiles specified by the experts and we transform them using the CDF of the decision maker. So we take the CDF of the decision maker at that quantile and call that value X. And that transforms these quantiles from whatever scale they were on originally to being between 0 and 1. So all of the X's will be between 0 and 1. So now they're all on the same scale. But we want to use this hierarchical model, which is assuming things are normal. So then we take the logit of the X's, so log of X over 1 minus X, and that transforms them back onto the whole real line. So whatever scale the Q's were on originally, the Z's are now on the whole real line. And we can use that hierarchical model and we can put in some sort of standard prior distributions for the decision maker and not worry too much about those. And then following the reconciliation, so following the aggregator, the Bayesian hierarchical model, we just back transform by using the inverse of those transformations there. So whenever I fit a model, all of the elicited quantities are going to go through this standardization process, then we'll do the Bayesian aggregation, and then we'll back transform in order to then look at how good they are. How do we choose the CDF for the parameter of interest for the decision maker, Fj? Well, if the decision maker is not an expert, then we could choose a relatively flat prior for them over the full range of values for theta j given by the experts. So you look across what's the sort of smallest value that any of the experts would thought plausible, what's the largest value that any of the experts thought plausible. You might add some overshoots, and then you choose a flat decision maker prior over that range. Okay, so that's the idea. That's all the ideas done. So now we'll just have a look at a few examples of this. So first of all, this is one of Willie's studies. So Willie could talk a lot more authoritatively about this than me, but I have read the papers that came out of this, and so I've tried to pick out information which I hope is true. So this was part of a project that Willie undertook to identify a cost-effective means of early detection of progressive erosion and in embankment dams. And the paper told me that the aim of the study was to aid management of erosion in these dams. In the data set, which is available as part of the Delphi database, we have data from 11 experts, which naturally fall into 3 groups and 11 seed questions. So the grouping in this case is essentially the background of the experts. So we have some academic experts, and we have different types of engineers who come from different organizations, and they separate nicely into 3 groups. And so I'm going to look at this Bayesian aggregation on the 11 seed questions. And of course, that's quite nice because we know the true values of the seed questions, so we can see how well we're doing. Because this original study used the classical method, Willie elicited 5%, 50%, and 95% quantiles. So L is the 5% quantile, U is the 95% quantile. And as I say, the original aggregation was performed using the classical method. So as an alternative, we're now going to look at what the aggregation would have looked like had we used this Bayesian hierarchical approach that I've just been through. And there it is. So along the x-axis, I've got each of the 11 seed variables. up the y-axis, I've got the values of those seed variables. So the red x's are the true values of the seed variables. The blue dots are the posterior means of the decision maker's posterior distribution. So this is our aggregated distribution, our reconciled distribution. And then the length of the vertical lines, these are 95% symmetrical posterior intervals. So they're 90% posterior intervals for the seed question. So in theory, 9 out of 10 of these should contain the true answers on average, if it's a well-calibrated distribution. Hopefully what you can see here is that just by eye, this doesn't look like there's too much bias going on in the method. We've got true values which are both above and below the posterior median. And we've also got true values which are both in the center of the distribution and some which are closer to the tails as well. So on these 11 values here, it looks like something reasonable might be going on. But is that because all the experts were particularly good in this particular study? Now, this is a tiny plot, so don't worry about seeing too much detail on this plot here. We've got each of the 11 seed questions. The x-axis now is each of the 11 experts. And then on the very right-hand side, the very final one is the aggregated distribution. And the dashed horizontal line there is the true value of the seed variable. For each of the experts and for the Bayesian aggregation, we've got median and 90% interval. Hopefully what you can see is that most of the experts are absolutely terrible. Most of the experts, most of the time, give very narrow intervals which don't contain the true value of the variable. Whereas using the aggregation, we've managed to capture the true value of the variable most of the time. And we've done that, as we often do in aggregation methods, by essentially having a much wider uncertainty in the aggregated distribution than the individual experts give. The Bayesian aggregation has worked out that the experts are overconfident and has essentially pulled the uncertainty wider to account for that. So the true value of the seed variables is within the aggregated distribution, but is almost never within individual expert distributions. So rather than just fit it to that single study, I then had to go fitting it to the Delphi database of studies. So Roger sent me the updated one, but this isn't the results from the updated one. This is the results from the older studies, so the 45 older studies. I haven't yet managed to get the updated one into the form I need to run this thing, and it will take a little while to run. So this is the slightly older study, so there will be a new version of this plot at some stage in the future. So on the left-hand side, in each of these plots, I've got Bayesian aggregation on the y-axis, and then on the x-axis, I've got equal weights on the left-hand side, a randomly selected single expert from each study in the middle plot, and the optimized decision maker from the classical method, global weights. I'm plotting the log scores, which is a proper scoring rule for each of the seed variables. So it's a proper scoring rule. It balances off the sort of calibration of predictions against the sharpness of the predictions, and it works nicely for continuous variables. So essentially, a higher log score means better predictions, a lower log score is poorer predictions. So what you'll see is in the equal weights one, the vast majority of points are above the line, which means the Bayesian aggregation gives a higher log score than equal weights. That's even more true if you just take a random expert from each of the studies. It's a little bit less clear with the classical method. Actually, approximately half of the crosses are above the line and half of them are below the line. But what you'll notice is that the ones above the line are a bit further above the line on average than the ones below the line. So when Bayesian aggregation does a bit better than the classical method, their log score, it tends to be a bit more better than when the classical method does better than this Bayesian aggregation. For these 45 studies, with me implementing these methods in a slightly vanilla way. So to try and put some numbers on this as well as pictures, I looked at the probability given the 45 sets of log scores from these 45 studies. So I've got essentially a paired samples test going on here. What's the probability that Bayesian aggregation gives a higher mean log score overall in the population? So if we had more than these 45 studies, it's 99.9% when compared to equal weights. So we're pretty sure we're better than equal weights. It's 99.99% when compared to a random expert. So based on log score, we're pretty sure we're better than a random expert. And it's a little bit less conclusive with the classical method, but based on the log score, it's 66.1% compared to the classical method. So this is a Bayesian. This is a sort of Bayesian version of a p-value from a paired samples t-test using these log scores. That's essentially a way of thinking about those numbers there. So that was all for continuous quantities, which is what we almost always think of when we think about aggregating expert judgments. But in both of these projects, Credo and Holy Food, we're also going to be trying to aggregate or reconcile probabilities, so a single probability given by an expert for a unique event. So if I've got a unique binary event and I can't think about a suitable population of similar events, all I can reasonably ask the expert for is the probability that the event is going to happen. So we've got binary events xj for some number of events, and we think of these as being Bernoulli with some pj, the probability that this binary event is going to happen. Is this water pumping station going to fail in this particular flood at this particular time? So pj's are just the probability that the pumping station fails. Again, if we ask individual experts for their probabilities that the pumping station fails, and we group those experts by their rationales in a probabilistic Delphi method, then what I'll get here is P for expert I in group J for binary event, group G for binary event J. And we can set up a similar hierarchical model as we did for continuous quantities. So now the probability from expert I in group G comes from, well, it's a probability, so a beta distribution is suitable. And we've parameterized this beta distribution so that these parameters have some nice interpretations. In particular, we can think of this n here as a within group sample size. So how much information is my expert using in order to give this probability? What equivalent sample size do they have in their head to base their probability on? So it's a sort of measure of their uncertainty. And P is just the mean. So this is the mean of these probabilities. So this is the individual probabilities. These would be the group level probabilities. And in the hierarchical model, they would form the second level of the hierarchy. And then Pj is going to be the overall probability for this binary event. So this is going to be the decision maker probability that comes out at the end. And so we also need a prior distribution on that one, which should go down here, but for some reason I put it slightly later. We can also learn about the information, the uncertainty of each of the individual experts by giving these within and between group sample sizes prior distributions as well. These are positive, so I'm giving them gamma prior distributions. And these hyperparameters here, the A's and the B's, would then control two things. They'd control essentially how uncertain each expert is in terms of the information they're giving us. So what sort of prior sample size is it equivalent to? But it's also going to control the correlation between the probabilities of individual experts, both within the groups and between the groups. So we can then use those to tweak how dependent the probabilities we think the experts are giving us are. How close to independence are they, or how close to just being essentially the same probability are they? And that's what those hyperparameters are going to help us to determine. And then the final level of the hierarchy, which should have been on the previous slide, would just be the decision maker level, giving a prior to the probability that the binary event is equal to 1. And if the decision maker doesn't do anything, we could give them a uniform on 0, 1, or equivalently a beta 1, 1 prior. And then the reconciled probability, when the decision maker then has observed each of the probabilities given by the experts, it's just the posterior predictive probability that the binary event is equal to 1. Or in other words, we can get samples from this bottom level, the PJ level in our hierarchy from our MCMC scheme, and it's just the average probability from those samples. So it's really easy to work out when we take samples from the posterior distribution using MCMC methods. Okay, so very briefly an example of this, and then I'll wrap up. So in Credo, one of the things that we needed to elicit was the probability that floodwater overtops a barrier outside a water pumping station. These are fictional numbers because I wasn't allowed to give you the real numbers that we elicited from the experts. For some reason, they were confidential. So let's suppose we had 10 employees of the water company. Here are the 10. These are the probabilities that they gave. And based on their rationales, we've grouped them into groups 1 and 2 because these 8 experts here used similar rationales to come to their probability judgments, whereas these 2 experts used different rationales. So they used the same as each other, but different everyone else. What you can see is that the experts in group 1 gave consistently higher probabilities, much higher probabilities to the event than experts in group 2. So if we just took the average of these probabilities, we'd get 0.35. The average of the 8 experts in group 1 is 0.41. The average of the 2 experts in group 2 is 0.1. If we use the Bayesian aggregation with sensibly chosen hyperparameters in the prior distributions, we ended up getting a reconciled probability of 0.3 there. So you'll see it's a bit lower than if you just take the average, and that's because we have correlated experts within each group. Essentially, the reconciled distribution is more evenly weighting the 2 groups than it is evenly weighting the 10 experts. So it's essentially saying the 8 experts in the first group are highly correlated with one another, so we give that slightly less than 8 out of 10 of the weight, is a way of thinking about what's happened there. The decision maker's prior does have some effect on your posterior probability in this case. So I've got different decision maker priors given by the different colored lines here. And we've plotted the posterior probability. And we've plotted that against the prior sample size that we say the experts are using. So 200 here would be a prior sample size of 100 for each of the experts. 100 would be a prior sample size of 50. And here's a prior sample size of 1. So what you see is that as you give more trust to the experts and give more certainty to their judgments, then the decision maker's prior distribution has less of an effect on the aggregated probability. So essentially, you have to be able to assume that your experts know something, otherwise you're going to return just something close to the decision maker's prior distribution in the end. In terms of the control that you have over the correlations between the probabilities given by the experts, so again, these are the hyper prior parameters for the n parameters, the prior sample sizes in the model. Essentially, what you can see, all I really want to show from this plot is within a group, you could choose correlations between the experts of anything between about 0.3 all the way up to 1 by sensibly calibrating your prior parameters. So whatever you think about how correlated these experts are, you can incorporate that within this hierarchical model structure. Okay, so that's everything really. So in summary, it can be challenging to conduct elicitation using my preferred method, the Sheffield method, particularly in multidisciplinary projects where people have opinions, even though their opinions aren't often based on much. Quite like the probabilistic Delphi method because it retains lots of these elements of interaction between the experts while getting over some people's concerns about too much interaction between the experts. Hopefully, you've seen that Bayesian hierarchical modeling can be used to reconcile the elicited distributions and also probabilities for binary events, which is something which is a little different than what most people do. And through this approach, we can take into account the dependence between the judgments given by different experts, and in particular, this idea that experts using similar rationales or with similar backgrounds will be given more correlated information than experts who are using very different rationales. Okay, that's it. And if you're interested, that's the archive paper at the bottom. I'll stop sharing and also stop recording.